Imagine for a moment that you're standing outside on a clear, starlit night, gazing up at the seemingly peaceful cosmos above, when suddenly, without warning, without even the faintest whisper of light or sound, an invisible predator tears through our solar system at nearly 3 million miles per hour, its gravitational claws reaching out across millions of miles, capable of shredding planets like tissue paper and hurling entire star systems into the cosmic abyss. This isn't science fiction. This is the terrifying reality of rogue black holes, the universe's most elusive and dangerous wanderers that are right now, at this very moment, hunting through the darkness of space. And what makes them truly nightmarish is that we can't see them coming. Tonight, we're going to embark on a journey into the most spine-chilling corners of astrophysics, where we'll discover that our universe is populated by countless invisible monsters, each one a stellar corpse so dense that it warps the very fabric of reality around itself. And these cosmic predators didn't just appear out of nowhere. They were created through some of the most violent and catastrophic events the universe has ever witnessed, born from the death throes of massive stars that exploded with such tremendous force that they literally kicked their own collapsed cores out of their home galaxies, sending them careening through space at velocities that would make your head spin. What we're dealing with here isn't just your typical black hole, safely anchored at the center of a galaxy where it feeds on the cosmic debris that spirals into its accretion disk. No, we're talking about cosmic refugees, stellar remnants that have been violently ejected from their birthplaces and now roam the vast emptiness between galaxies like interstellar nomads, invisible to our telescopes because they emit no light, produce no heat, and reveal their presence only through the gravitational carnage they leave in their wake. To truly understand the horror of what a rogue black hole represents, you need to grasp the sheer impossibility of their existence. Imagine trying to compress the entire mass of our Sun, which weighs approximately 330,000 times more than Earth, down into a sphere just 6 kilometers across, creating an object so dense that a teaspoon of its material would weigh as much as Mount Everest. And now imagine that this cosmic monster, this gravitational predator that bends light itself around its event horizon, is moving through space at speeds that would allow it to travel from Earth to Mars in just a few hours, completely invisible to our detection methods until the moment it begins to tear apart everything in its path. The birth of a rogue black hole is a story written in cosmic violence, beginning with a star so massive that it makes our Sun look like a grain of sand by comparison. We're talking about stellar giants that are 20, 30, even 50 times more massive than our own star, burning through their nuclear fuel at such a furious rate that they live fast and die young, existing for only a few million years before reaching the inevitable moment when their cores can no longer sustain the nuclear fusion that keeps them from collapsing under their own immense gravitational weight. When these stellar behemoths finally exhaust their fuel, what happens next is nothing short of apocalyptic. The star's core collapses in on itself in less than a second, creating a shockwave that races outward through the star's outer layers at speeds approaching 30,000 kilometers per second. And when this shockwave reaches the star's surface, the entire star explodes in what we call a supernova, an explosion so bright that it can outshine an entire galaxy containing 100 billion stars, visible from billions of light years away. And in that moment of cosmic destruction, something extraordinary and terrifying happens. The explosion isn't perfectly symmetrical. Cosmic events never are. And if a supernova blast occurs with even the slightest asymmetry, if one side of the explosion is just fractionally more powerful than the other, the newly formed black hole receives what astronomers call a natal kick, a gravitational recoil that can launch it out of its home galaxy at velocities ranging from hundreds to thousands of kilometers per second, fast enough to escape the gravitational embrace of even the most massive galaxies and begin its eternal journey through the cosmic void. Picture this scene unfolding across the universe. Every few seconds, somewhere in the observable cosmos, a massive star dies in a supernova explosion, and a significant fraction of these deaths results in the birth of a new rogue black hole, each one kicked out into space to begin its solitary hunt through the darkness. And when you multiply this process across the 13.8 billion year history of our universe, Across the trillions of galaxies that populate the cosmic web, you begin to realize that space is absolutely teeming with these invisible predators, with some estimates suggesting that there could be billions or even trillions of rogue black holes wandering through the universe at any given moment, outnumbering the stars themselves in some regions of space. Retry. The hunt begins the moment a rogue black hole is born. And what makes these cosmic predators so utterly terrifying is not just their immense gravitational power, but their complete and total invisibility. Imagine a hunter so perfectly camouflaged that it casts no shadow, makes no sound, leaves no trace of its passage except for the devastation it leaves behind. And this is exactly what we're dealing with when we talk about rogue black holes moving through space at millions of miles per hour. Their presence detectable only when they begin to gravitationally interact with matter, bending light around themselves in a phenomenon called gravitational lensing, or when they encounter a star system and begin the process of systematically destroying everything in their path. To understand how a rogue black hole hunts, you need to visualize its gravitational influence as extending far beyond its event horizon, that point of no return where even light cannot escape, because the gravitational field of a black hole reaches out across vast distances, creating what astronomers call a sphere of influence that can extend for thousands or even millions of times the black hole's physical size. And as this invisible predator moves through space, it's constantly probing the cosmic environment around it, its gravitational tentacles reaching out to feel for any nearby matter, any unfortunate star, planet, or cosmic debris that might cross its path. When a rogue black hole encounters a star system, the destruction doesn't happen all at once. Instead, it unfolds like a cosmic horror story in slow motion, beginning when the black hole is still light years away and its gravitational influence starts to subtly perturb the orbits of the outermost planets, causing them to drift from their stable paths and begin spiraling either inward toward their star or outward into the cold depths of space. And this is just the beginning of the carnage because, as the rogue black hole continues its relentless approach, its gravitational field grows stronger and stronger, reaching out to grab hold of comets, asteroids, and eventually the planets themselves. The physics of what happens when a rogue black hole encounters a solar system like ours is simultaneously beautiful and horrifying. Imagine our Jupiter, that massive gas giant that acts as a gravitational shepherd for our solar system, suddenly finding itself caught in a cosmic tug-of-war between the sun's familiar gravitational embrace and the irresistible pull of an approaching black hole. And as the rogue predator draws closer, Jupiter's orbit begins to stretch and distort, sometimes elongating into a highly elliptical path that sends it careening toward the inner solar system on a collision course with the terrestrial planets, or alternatively, flinging it outward into interstellar space where it becomes a frozen, rogue planet wandering the cosmic void forever. But the true nightmare scenario occurs when a rogue black hole doesn't just pass near a star system, but actually captures it, turning what was once a stable, life-giving star into a cosmic lighthouse of destruction. Picture our sun being torn from its gravitational moorings and dragged into orbit around an invisible predator, its outer layers stretched and heated by tidal forces until they begin to glow with the fierce radiation of an accretion disk, transforming our peaceful yellow star into a screaming beacon of X-rays and gamma radiation that would sterilize any planets that somehow manage to remain in orbit around it. The hunting patterns of rogue black holes are as varied as they are terrifying, because these cosmic predators don't all behave the same way. Some are lone wolves, solitary hunters that prowl the empty spaces between galaxies, feeding only occasionally when they happen to encounter a wandering star or a stray planet that has been ejected from its home system, while others travel in packs, binary or even triple black hole systems that were created when multiple massive stars in a cluster died and their resulting black holes remained gravitationally bound to each other, creating cosmic death squads that sweep through space like interstellar combined harvesters, their combined gravitational fields capable of shredding entire star clusters and scattering their stellar inhabitants across the galaxy. What makes the hunt even more insidious is that rogue black holes don't need to make direct contact with their prey to destroy it. The gravitational influence of a passing black hole can be enough to destabilize an entire planetary system, causing planets to migrate inward or outward from their stars, triggering climate changes that could end civilizations, or even ejecting planets from their solar systems entirely. turning them into rogue worlds that drift through space in perpetual darkness and cold. And this means that a rogue black hole could hunt and kill without ever coming close enough to its victims to reveal its presence through gravitational lensing or other observable effects. The speed at which these cosmic predators move through space adds another layer of terror to their hunting behavior. Because unlike the black holes we're familiar with at the centers of galaxies, which remain relatively stationary and allow matter to gradually spiral into their accretion disks over millions or billions of years, rogue black holes are moving so fast that their interactions with matter are violent, sudden, and catastrophic. Imagine a black hole traveling at 1,000 kilometers per second encountering a star, and instead of the leisurely dance of orbital decay that we might expect, the star is torn apart in a matter of days or weeks, its material scattered across space in long, luminous streams that stretch behind the black hole like the tail of a deadly comet. And by the time astronomers on a distant planet notice the sudden flare of light from the dying star, the rogue black hole has already moved on to its next victim, leaving behind only a cooling cloud of stellar debris and the gravitational echoes of its passage. Retry. The detection of rogue black holes represents one of the greatest challenges in modern astronomy, a cosmic game of hide-and-seek where the stakes couldn't be higher and the hunters are searching for predators that are, by their very nature, completely invisible to every instrument we've ever built. Imagine trying to find a burglar in your house when that burglar casts no shadow, makes no sound, leaves no fingerprints, and can only be detected by the subtle way the floorboards creak under their weight. And you begin to understand the monumental task that astronomers face when they attempt to track these gravitational ghosts as they prowl through the darkness of space. The primary method we use to hunt for rogue black holes is called gravitational microlensing, a technique so elegant and so subtle that it borders on the miraculous. When a rogue black hole passes directly between Earth and a distant star, its immense gravitational field acts like a cosmic magnifying glass, bending and focusing the light from the background star in such a way that, from our perspective, the star appears to brighten dramatically for a period of weeks or months before gradually returning to its normal luminosity. And this temporary brightening event, this cosmic spotlight effect, is often the only evidence we have that a rogue black hole has passed through our line of sight. But here's where the detection game becomes truly challenging. A typical microlensing event caused by a rogue black hole might last anywhere from a few weeks to several months, and during that time, the black hole itself remains completely invisible, revealing its presence only through the way it manipulates the light from stars that lie millions or billions of times farther away. And to make matters even more complicated, similar lensing effects can be caused by ordinary stars, brown dwarfs, planets, or even clumps of dark matter, which means that astronomers must carefully analyze the precise shape and duration of each brightening curve to determine whether they are looking at the signature of a rogue black hole or some other cosmic object. The mathematics behind gravitational microlensing are both beautiful and terrifying in their implications. Einstein's equations tell us that the duration of a microlensing event is directly related to the mass of the lensing object and its distance from Earth, which means that rogue black holes, with their tremendous masses compressed into infinitesimally small volumes, create microlensing signatures that are distinctly different from those produced by normal stars or planets. And when astronomers detect a microlensing event that lasts for months and shows the characteristic smooth, symmetrical brightening curve that indicates a very massive, compact object, they know they may have caught a glimpse of one of these cosmic predators in action. The search for rogue black holes has led to the development of some of the most sophisticated astronomical survey projects ever conceived. Massive robotic telescopes that photograph millions of stars night after night, looking for the telltale signs of gravitational lensing events, and computer algorithms that can sift through terabytes of data to identify the subtle variations in stellar brightness that might indicate the passage of an invisible predator. And what these surveys have revealed is both fascinating and deeply unsettling, because while we've only definitively identified a handful of rogue black hole candidates through microlensing, the statistics suggest that these events should be much more common than we're currently detecting, which means that either our detection methods are missing most of these cosmic predators, or the universe is even more densely populated with invisible black holes than our most conservative estimates suggest. One of the most famous potential rogue black hole detections occurred in 2022, when the Hubble Space Telescope identified a microlensing event designated OGLE 2011 BLG0462, where a background star was magnified by what appeared to be a black hole with a mass roughly 7 times that of our Sun, moving through space at approximately 45 kilometers per second. And what made this detection particularly significant was that follow-up observations revealed no visible companion star or accretion disk around the lensing object, strongly suggesting that astronomers had indeed caught their first confirmed glimpse of a rogue black hole drifting through the galaxy like a gravitational phantom. But the true horror of rogue black hole detection lies not in what we found, but in what we haven't found. Computer simulations of galactic evolution predict that our Milky Way galaxy alone should contain somewhere between 100 million and 1 billion rogue black holes, wandering through the galactic disk and halo like invisible wolves among sheep. And yet we detected only a tiny fraction of this predicted population, which means that right now, as you're listening to these words, there could be dozens or even hundreds of rogue black holes within just a few light years of our solar system, their gravitational fields reaching out through space like invisible tentacles, waiting for the moment when some unlucky star or planet wanders too close to their event horizon. The detection challenges are compounded by the fact that rogue black holes don't behave like the supermassive black holes we find at the centers of galaxies. They don't have bright accretion disks fed by a steady stream of infalling matter. They don't produce powerful jets of high-energy particles. And they don't announce their presence with the spectacular light shows that make other black holes visible across billions of light-years. Instead, they move through space like cosmic stealth bombers, detectable only through their gravitational influence on other objects. And this means that our current detection methods are biased toward finding only those rogue black holes that happen to pass directly between Earth and a background star, which represents an infinitesimally small fraction of all the rogue black holes that must be out there. Recent advances in gravitational wave astronomy have opened up new possibilities for detecting rogue black holes. Because when two of these cosmic predators encounter each other in the depths of space, they spiral together in a deadly dance that warps space-time itself, sending ripples through the fabric of reality that we can detect with instruments like LIGO and Virgo. And some of the gravitational wave signals we've detected may indeed come from merging rogue black holes that were kicked out of their home galaxies billions of years ago and have been wandering through space ever since, occasionally finding each other in the cosmic darkness and engaging in these apocalyptic collisions that announce their presence to the entire universe through the gravitational waves they produce. But even this detection method has its limitations, because it only works when rogue black holes happen to collide with each other, an event that might occur only once every few million years in a region the size of our local galactic neighborhood. Retry. The cosmic implications of rogue black holes extend far beyond their individual hunting behaviors, because these invisible predators are actively reshaping the large-scale structure of the universe itself, acting as agents of galactic destruction and cosmic evolution on scales that dwarf even our most ambitious science fiction nightmares. Imagine billions of these gravitational monsters roaming through the vast spaces between galaxies, occasionally encountering smaller dwarf galaxies or globular star clusters and systematically tearing them apart star by star, scattering their stellar populations across millions of light-years and leaving behind only faint trails of cosmic debris as evidence of the civilizations and worlds that once called those systems home. The mathematics of rogue black hole encounters with galactic structures paint a picture of cosmic carnage that unfolds over millions and billions of years. When a rogue black hole with a mass of 10 or 20 times that of our Sun encounters a small galaxy containing perhaps a billion stars, the gravitational interaction doesn't result in a single catastrophic collision, but rather in a slow-motion dance of destruction that plays out over hundreds of millions of years, with the rogue black hole acting like a cosmic wrecking ball, its passage through the galaxy's spiral arms disrupting stellar orbits, triggering waves of star formation in some regions while completely evacuating stars from others, and ultimately leaving the galaxy a hollow shell of its former self, stripped of much of its stellar population and transformed from a vibrant star-forming system into a cosmic graveyard. But perhaps the most terrifying aspect of rogue black holes is their potential impact on the future evolution of life in the universe, because these invisible predators represent a constant, ever-present threat to any civilization that might arise on planets orbiting stars in their path. Picture an advanced alien civilization that has spent millions of years developing technology, art, culture, and knowledge, only to have their entire solar system disrupted by the passage of a rogue black hole that they never saw coming, their star torn from its stable position and either flung into interstellar space or dragged into a death spiral around the invisible predator. And in either case, any planets in that system would face extinction through freezing, radiation bombardment, or tidal destruction, erasing millions of years of evolution and development in a cosmic instant. The statistical probability of a rogue black hole encounter with our own solar system is both reassuring and deeply unsettling. Current estimates suggest that the likelihood of a rogue black hole passing close enough to our Sun to significantly disrupt planetary orbits is extremely small over human timescales, perhaps once every few billion years. But when we consider the vast number of rogue black holes that may be wandering through our galaxy, and the fact that even a distant passage could have subtle effects on the outer regions of our solar system, the picture becomes more complex and more frightening. Because a rogue black hole doesn't need to make a direct hit to cause problems. It could pass through the Oort cloud, that vast sphere of comets that surrounds our solar system at distances of up to 100,000 astronomical units from the Sun, and gravitationally perturb thousands or millions of these icy bodies, sending them careening toward the inner solar system in a cosmic bombardment that could last for hundreds of thousands of years. The role of rogue black holes in cosmic evolution extends beyond their destructive capabilities, because these wandering predators also serve as agents of galactic mixing and stellar redistribution, carrying matter and energy from one region of the universe to another, and helping to homogenize the chemical composition of intergalactic space. When a rogue black hole tears apart a star, it doesn't consume all of the stellar material, instead scattering much of it across vast distances in long, glowing streams that eventually cool and condense into new generations of stars and planets, carrying with them the heavy elements forged in the nuclear furnaces of the destroyed star and seeding distant regions of space with the raw materials necessary for the formation of rocky planets and, potentially, life itself. Recent computer simulations have revealed that rogue black holes may have played a crucial role in the early universe, when galaxies were smaller, closer together, and more prone to gravitational interactions that could eject black holes from their host systems. During this cosmic adolescence, roughly 8 to 10 billion years ago, the rate of rogue black hole production may have been much higher than it is today, and these early cosmic predators may have been responsible for preventing the formation of many small galaxies by disrupting star-forming regions and scattering their material into intergalactic space, effectively acting as a cosmic population control mechanism that shaped the galaxy mass function we observe in the universe today. The discovery of hypervelocity stars, individual stars that have been accelerated to such extreme speeds that they are escaping our galaxy entirely, provides indirect evidence for the existence of rogue black holes, because the gravitational slingshot effect required to accelerate a star to escape velocity can only be achieved through close encounters with extremely massive, compact objects. And while supermassive black holes at galactic centers can certainly provide this acceleration, many hypervelocity stars are found in regions of the galaxy where such encounters seem unlikely, suggesting that their extreme speeds may have been imparted by close encounters with wandering rogue black holes that have since moved on to terrorize other parts of the galaxy. The implications for the far future of our universe are particularly sobering when we consider the role that rogue black holes will play in the heat-death scenario. As the universe continues to expand and cool, star formation will eventually cease, existing stars will burn out and die, and the cosmos will enter a phase dominated by stellar remnants like white dwarfs, neutron stars, and black holes. And during this dark era, rogue black holes will continue their eternal hunt through space, occasionally encountering and consuming the last remaining sources of matter and energy, slowly growing in mass and size until they become the dominant gravitational influences in a cold, dark, and nearly empty universe. The final predators stalking through a cosmic wasteland where nothing remains but the fading echoes of a once vibrant cosmos filled with stars, planets, and perhaps even life itself. As we stand at the precipice of a new era in astronomical discovery, the hunt for rogue black holes is entering its most critical and exciting phase, with revolutionary new technologies and detection methods promising to finally illuminate the dark corners of our universe where these cosmic predators have been hiding for billions of years. Imagine a future where space-based gravitational wave detectors with arms stretching millions of kilometers can detect the subtle space-time ripples created When rogue black holes pass through regions of space containing dark matter or cosmic dust, or advanced AI systems that can analyze the motion of billions of stars simultaneously to identify the gravitational perturbations that betray the presence of an invisible predator lurking nearby. And you begin to glimpse the unprecedented opportunities that lie ahead for astronomers determined to catalog and track these wandering monsters. The next generation of astronomical surveys, including the Vera Rubin Observatory's Legacy Survey of Space and Time, will photograph the entire visible sky every few nights for 10 years, creating an unprecedented database of stellar motion and brightness variations that will allow astronomers to detect gravitational microlensing events with a sensitivity and completeness that was unimaginable just a decade ago. This systematic approach to rogue black hole hunting will finally allow us to move beyond the current situation where we detected only a handful of candidates to a comprehensive census of the invisible predators that share our galaxy, and the implications of what we might find are both thrilling and terrifying. Because if our theoretical predictions are correct, we're about to discover that we live in a universe far more dangerous and dynamic than we ever imagined. The European Space Agency's Gaia mission, which has already measured the precise positions and velocities of over 1.8 billion stars in our galaxy, is providing astronomers with the data they need to identify stars that are moving in ways that suggest they've had close encounters with massive, invisible objects. When a star passes near a rogue black hole, the gravitational interaction can alter its trajectory in subtle but measurable ways, and by carefully analyzing the motion of millions of stars over time, astronomers are beginning to identify populations of stars that show the characteristic velocity signatures of rogue black hole encounters, like cosmic forensic investigators piecing together evidence of crimes committed by invisible perpetrators. But perhaps the most revolutionary development in rogue black hole detection is the emergence of gravitational wave astronomy as a tool for probing the dark matter content of the universe. When gravitational waves from distant black hole mergers pass through regions of space containing rogue black holes, the waves are subtly lensed and distorted by the gravitational fields of these invisible objects, creating characteristic patterns in the gravitational wave signals that can reveal the presence and properties of intervening rogue black holes. And this technique, known as gravitational wave lensing, promises to open up entirely new windows into the hidden population of cosmic predators that populate the space between galaxies. The technological challenges of detecting and tracking rogue black holes are driving innovations that extend far beyond astronomy. The need to process vast amounts of data in real time to identify transient microlensing events is pushing the boundaries of machine learning and artificial intelligence, while the requirement for ultra-precise measurements of stellar positions and velocities is leading to advances in space-based interferometry and quantum sensing technologies that will have applications ranging from fundamental physics research to next-generation GPS systems, and the computational models needed to simulate the complex interactions between rogue black holes and galactic structures are driving the development of exascale supercomputers capable of performing calculations that would have been impossible just a few years ago. The search for rogue black holes is also revealing unexpected connections between these cosmic predators and some of the most fundamental questions in physics and cosmology. The distribution of rogue black holes throughout the universe provides clues about the nature of dark matter, the formation and evolution of the first stars and galaxies, and even the ultimate fate of our cosmos. And as we develop more sophisticated methods for detecting and studying these invisible wanderers, we're gaining new insights into the processes that shape the universe we see today and continue to drive its evolution on the largest scales. Recent theoretical work has suggested that some rogue black holes may not be solitary hunters at all, but rather members of complex dynamical systems that include pairs or even small groups of black holes that were ejected together from their host galaxies and continue to orbit around each other as they wander through space. These binary rogue black holes would be particularly dangerous to any star system unlucky enough to encounter them, because their combined gravitational field would be even more disruptive than that of a single black hole, capable of completely destabilizing planetary orbits at much greater distances and potentially triggering the ejection of entire planets from their solar systems. And the detection of gravitational waves from the eventual merger of such binary systems would provide astronomers with a treasure trove of information about the properties and prevalence of these cosmic death squads. As our understanding of rogue black holes continues to evolve, we're beginning to realize that these cosmic predators may play a crucial role in regulating star formation and galactic evolution throughout the universe. By disrupting star-forming regions and scattering stellar populations, Rogue black holes act as a kind of cosmic thermostat, preventing galaxies from forming stars too rapidly and helping to maintain the delicate balance between star formation and stellar death that has allowed the universe to remain active and dynamic for billions of years. And this regulatory function may be one of the key factors that has made the existence of complex structures like galaxies, solar systems, and ultimately life itself possible in our universe. The future of rogue black hole research promises to be filled with discoveries that will challenge our understanding of cosmic evolution and our place in the universe. As we develop the ability to detect and track these invisible predators in real time, we may discover that they are more numerous and more active than we currently suspect, or we may find that they follow predictable migration patterns that could allow us to forecast potential encounters with our own solar system millions of years in advance, giving future civilizations the time they need to develop protective technologies or evacuation strategies. And regardless of what we discover, one thing is certain: the hunt for rogue black holes will continue to push the boundaries of human knowledge and technology, driving us to develop ever more sophisticated methods for exploring the hidden darkness that lies between the stars and revealing the invisible architecture of destruction and creation that shapes our cosmic neighborhood. The universe we inhabit is far stranger and more dangerous than the peaceful night sky suggests, filled with invisible predators that hunt through the darkness of space, each one a gravitational monster capable of destroying entire solar systems while remaining completely undetectable until the moment they strike. Rogue black holes represent one of the greatest mysteries and threats in modern astronomy. Cosmic wanderers born from stellar violence and kicked into exile to roam the vast emptiness between galaxies for billions of years. As we stand on the threshold of revolutionary new detection technologies, we're finally beginning to illuminate these dark corners of our universe and discover that we live in a cosmos populated by countless invisible hunters. The hunt for rogue black holes continues, and with each new detection, we come closer to understanding the true nature of the cosmic predators that share our galaxy, forever changing our perspective on the universe we call home. Retry.